In this video, I'm going to talk about a very interesting concept called the nth roots of a complex number. And so what we are asking is the question, suppose I have a complex number z naught, which in polar form is given by r naught times e to the j theta naught. And suppose n is an integer. What are the nth roots of this complex number z naught? So what exactly does that mean? What that means is we are asking for a number or a complex number z, which is the, let's say, which is the nth root of z naught, or equivalently, we are asking for complex number z such that if you raise z to power n, you get any given complex number called z naught, right? Now, it turns out that there are n such numbers z, which if you raise to power n will give you any given complex number z naught. And to see this, this is actually a natural extension of something that you are fairly used to. So for example, if you take let's take a simple example. Suppose z is the complex number 4, which is 4 plus j0, right? Or z naught is 4 plus j0. And let's say n is 2. I asked you what are the square roots of 4. Now, you know that both 2 and negative 2, when you square them, are going to give you 4, right? So there are two possibilities for the square root of 4, but by convention, we usually take the positive value as the square root of 4, but nevertheless, we say that there are two numbers which when you square are going to give you 4. In the same way, there are going to be n numbers, n complex numbers, which when you raise to power n are going to give you any given complex number z naught. And to see that, you can take this equation and think of this as the equation z to the n minus z naught is equal to 0. Right? Now, think of this as a polynomial in z. So the degree of this polynomial is n, and every nth degree polynomial has exactly n roots. Some of them may be complex, or maybe all of them may be complex, and so there are indeed n different values of z that will give you z naught when you raise them to power n. The question is, how do you find them? Okay, so since this is a somewhat important a topic, I will actually work through an example and then we'll try to generalize this. So here is an example. Let's say that we want to find all the third roots, or actually maybe we'll say, okay, third roots of the complex number 2 times e to the j pi over 3. Okay, so how can we find the cubed roots of the complex number 2 times e to the j pi over 3? Okay, so one obvious root is to say that I take the magnitude and I take 1/3, raise that to power 1/3, and then I take the face and I divide that by 3. So for example, the first root is pretty easy to see. It's given by, maybe I'll to make these numbers easier. So instead of 8, let's 2, let's say that we have 8 times e to the j pi over 3. So the first root you can see is 2 times e to the j pi over 9. Now, why is that a cubed root of z naught? You can see that if I take z and I raise that to power 3, I'm going to get 2 raised to power 3 times e to the j pi over 9 raised to power 3, but that's the same as multiplying the exponent by 3. And indeed, these two cancel out, and they're going to give you e to the j pi over 3, which is exactly what I have here. right? Well, how do we find the other two roots? And to find the other two roots, we need to use the fact that 8 times e to the j pi over 3 is the same as 8 times e to the j pi over 3 plus 2 pi. And it's also the same as 8 times e to the j pi over 3 plus 4 pi. Remember, we saw in an earlier video that if I add any integer multiple of 2 pi to the angle, the complex number remains unchanged. And you can see an use for that fact right now. So what we are going to do is this. We're going to take this complex number and try to find the cubed root of this by doing exactly what we did here, which is to take the magnitude, take the cubed root of that. That's going to give us a 2, but take the angle and divide that by 3. But notice now that when you divide this angle by 3, you're going to get the pi over 9 that we got earlier here. But you're also going to get an extra plus 2 pi over 3. And therefore, the second root so we'll call this as maybe, yeah, and the second root is going to be 2 times e to the j pi over 3 plus 2 pi divided by 3, which is 2 times e to the j pi over 9 plus 2 pi over 3. Indeed, this complex number is now different from this complex number. Okay, so these two are not the same because notice that there is an extra angle of 2 pi over 3, not 2 pi. So this complex number is indeed different from this complex number, and that's a cubed root of 8 times e to the j pi over 3. And you can find the third root by adding another 2 pi to this, right? So we take e to the j pi over 3 plus 4 pi divided by 3, and that's going to give you e to the j pi over 9 plus 4 pi over 3. And now you can ask me, okay, why did I stop at 4 pi? Why did you not go ahead and add 6 pi to it? Perhaps you'll get another root, right? And if you think about it, that's not going to happen, because if I add 6 pi, the next integer multiple of 2 pi, what's going to happen is I'm going to get a 6 pi over 3 here. But remember, 6 pi over 3 is the same as 2 pi. So that's nothing but 2 times e to the j pi over 9 plus 2 pi, which is exactly the same as e to the j pi over 9. So maybe I will remove this just now so that we don't get confused. So then the three roots are given by 2 times e to the j pi over 9, 2 times e to the j pi over 9 plus 2 pi over 3, and 2 times e to the j pi over 9 plus 4 pi over 3. If I had asked for the fifth roots of z0 instead of the third root, you can repeat the same procedure, but you would have to go 5 times, because each time you would be multiplying by 2 pi over 5, 4 pi over 5, 6 pi over 5, and 8 pi over 5. And then it would start to repeat when you get to 10 pi over 5. So you would get the 5 roots that way. Okay. So hopefully this idea is clear. So if this idea is clear, let's go ahead and generalize this. So we're going to generalize what we did in the example to find the nth roots of a complex number z0. So what we're going to say is this. So if you pick z to be r0 raised to power 1 over n, keeping in mind that you take only the positive nth roots of a real number, then that becomes the magnitude of each of the roots, and you take the angle theta naught and you add 2 pi times k and you divide this whole thing by n. And you do this for k starting from 0, 1 all the way up to n minus 1. And for each value of k, you will get a different complex number, and that will be a nth root of z naught. And again, to see why this will be an nth root of z naught, you can see that if you raise z to power n, what happens when we raise this to power n? The first term, when you raise it to power n, it's going to give you r naught. The second term, when you raise it to power n, is going to give you e to the j times this angle here multiplied by n, because you're raising it to power n. So that n and what's in the denominator is going to cancel out, and you get theta naught plus 2 pi times k. And we know that e to the j theta naught plus 2 pi times k is equal to r naught times e to the j theta naught, which is equal to z naught. In other words, for every one of these roots, so notice that, so we get a total of n roots by setting k to go from 0 to n minus 1. For every such value of k, you're going to get one root here, and when you raise that to power n, indeed you get the same complex number back. Okay, so this is how you find the nth roots of a complex number. Oops. Okay, I already worked out one example. In a separate video, I'm going to work out another example, and hopefully with all these, this concept becomes clear.